This is the PlayStation 5, a sleek, futuristic box hiding the result of one of the most ambitious global manufacturing operations ever attempted in consumer electronics. From the outside, it's a bold, iconic design. From the inside, it's a symphony of custom silicon, thermal science, and precision robotics. The journey of every PS5 begins with the brain, a custom AMD chip forged in microscopic layers of silicon. But what truly sets this console apart isn't just what it can do, it's how it was made. Building a PlayStation 5 isn't as simple as putting together parts in a factory. It's a high-wire act that stretches across hundreds of cities, with over 1,000 suppliers, and manufacturing facilities that run with the discipline of military operations. One hiccup, one delay, one single flaw in a component, and it can cost billions. This story is about how Sony built one of the most powerful consoles in history, and how they did it using one of the most dangerous substances ever used in consumer electronics, liquid metal. At the center of this machine is the APU, the Accelerated Processing Unit. It's a custom fusion of CPU and GPU designed by AMD, based on Zen 2 and RDNA2 architectures. But this chip is powerful. Too powerful, in fact, for traditional thermal paste. In most consoles or PCs, a gray paste is applied between the chip and the heatsink to help transfer heat. But for the PS5, Sony needed something better, way better, and that's where liquid metal comes in. Liquid metal has a much higher thermal conductivity than traditional paste, which means it can move heat away from the chip more effectively. That keeps the chip cooler, the console quieter, and the performance stable even during intense gaming sessions. It wasn't an easy decision. Engineers debated the risks for months. Liquid metal, while efficient, is a finicky substance. It's electrically conductive, which means a single droplet landing where it shouldn't can fry the entire board. It's also prone to movement over time, especially when the console is standing upright for long periods. So if Sony was going to make this leap, they had to engineer their way around every single weakness. This wasn't just about slapping on a high-performance cooling material. It required an entirely new hardware ecosystem. Sony had to design a custom foam barrier to contain the liquid metal and prevent it from spilling beyond the chip's edges. That foam had to be precision cut and thermally stable. It couldn't shrink, it couldn't deform, it couldn't fail, ever. Then came the challenge of applying the metal itself. This wasn't something human hands could do reliably. Liquid metal smears, it oxidizes, it can't be handled like paste. So the solution was robotics. A highly specialized robotic arm was developed just for this task. Not borrowed from other manufacturing lines, not repurposed. Built from the ground up with one job, to apply this volatile substance with a level of care normally reserved for semiconductor fabs. The robot uses a tiny needle-like applicator to deposit the liquid metal in a perfect pattern across the APU surface. Not too much, not too little, just the right amount to ensure maximum thermal transfer while maintaining isolation from the surrounding components. It then spreads it using a technique that resembles micro-squeegeeing, leveling out the surface so there are no bubbles, no streaks, no missed spots. And this all happens in an environment that's sterile, temperature-controlled, and monitored down to the micron. Sensors constantly verify the placement, the amount, and the spread of the liquid metal in real time. If anything deviates from the target, or even slightly, the machine halts. It's that sensitive. Once the liquid metal is in place, the massive aluminum heatsink is lowered into position with robotic arms. Again, precision matters. Even pressure must be applied across the entire contact surface to avoid air gaps. Air gaps mean hot spots. Hot spots mean noise, throttling, or worst of all, failure. To ensure nothing moves during shipping, foam pads are also placed around the APU area to hold everything securely in place. This is critical because if the console experiences a hard bump during transit, even the smallest shift in the heatsink could lead to misalignment, and that misalignment could disrupt cooling. There's also a consideration for long-term usage. Liquid metal tends to settle over time. Gravity can cause it to pool unevenly, especially if the console is positioned vertically. Sony's engineers took this into account when designing the containment system. The seal around the chip ensures the liquid metal stays exactly where it's needed, no matter how the console is stored or moved. And then there's oxidation. Liquid metal can react with air or other metals, forming a crusty layer that drastically reduces its thermal performance. To fight this, Sony's system ensures the metal is fully enclosed, isolated from the environment, sealed in a vacuum-tight thermal envelope. In total, the decision to use liquid metal in the PS5 wasn't just about performance, it was about pushing the boundaries of what a home console could be. Taking something that had previously only been used by custom PC builders and integrating it into a global supply chain with millions of units in production. It was a gamble, one that paid off, because it allowed Sony to deliver not just a more powerful console, but a quieter one, a more efficient one that stays cool under pressure and performs without compromise. It's the kind of detail most players will never see, and that's exactly the point. The best engineering often hides in plain sight, but here's the thing, liquid metal is also electrically conductive. If it leaks, even in the tiniest droplet, it can short-circuit the motherboard. That's game over for the console. So Sony couldn't just slap some on and call it a day, they needed an entirely new process. They needed robots. Not just any robots. A custom-built robotic arm, equipped with a microscopic sponge barrier system, designed to apply the liquid metal with such precision it can't leak. The arm dispenses just the right amount of liquid metal, spreads it evenly across the surface of the APU, and then seals it in with a foam barrier. It's a surgical process. Most people don't realize this, but if a PlayStation 5 is stored upright for too long, the liquid metal inside can slowly shift and pool unevenly. Over time, that causes overheating, throttling, and performance issues. That's why the robots aren't just designed to apply the liquid metal. They're built to make sure it's placed in a way that will remain stable for years, even if the console moves, even if it's shaken, even if it's flipped. That's only one part of the equation though, because once the APU and liquid metal system are in place, the rest of the machine needs to be built with matching precision. That happens in Kisarazu, Japan, home to a 30-meter-long robotic assembly line capable of producing one PS5 every 30 seconds. The factory is cleaner than a hospital operating room. 32 robotic arms perform the entire process, from motherboard assembly to final packaging. And every move is coordinated with ballet-like timing. No human hands touch the machine during assembly, but human engineers are always watching. They monitor the entire line, ready to intervene if anything strays from perfection. One of the most delicate tasks in the entire process is wiring. Flexible flat cables used to connect parts of the console used to be something only human hands could manage. But today, a 2.2-meter robotic arm does it faster and more precisely than any human ever could. It threads, folds, and places the cables with zero slack, zero waste, and zero error. Then comes the real heart. The massive heatsink and the liquid metal cooling system are mounted on top of the chip, locking in the thermal core. With the internals set, it's time to armor up. The iconic white side panels are injection molded and snapped into place. These aren't just for looks. The texture, the shape, and the vent placement are all designed for airflow, part of a carefully tuned thermal design. Every curve and ridge on the shell exists for a reason. It's built to keep the PS5 cool under pressure. And when that shell clicks in, it's a final seal on one of the most thermally efficient consoles ever made. But before a PS5 can leave the factory, it has to survive what some call the gauntlet. This is a brutal, unforgiving series of automated tests. Every port is checked, every button is pressed, the disk drive is tested, the software is flashed, then the console is powered on, and if a single thing goes wrong, it's pulled from the line. There are no spot checks here. Every single console is tested. That's not typical in electronics manufacturing, but Sony knows the stakes. A failure in the field isn't just bad PR, it's a broken experience for someone who saved up to buy one of these machines, and that's unacceptable. So what happens to the consoles that fail? They don't get shipped. They're analyzed, dissected, sometimes recycled. The margin for error is zero. And that's not a figure of speech. A console with a microscopic flaw in its liquid metal seal could fail 1,000 miles away in someone's home. That's why the robots in Kisarazu don't just build, they protect. All of this leads to a moment that most players never see. Finished, tested, boxed, the PS5s are loaded onto pallets and enter a global logistics network powered by predictive analytics. Ships, planes, trucks, all moving in sync. Sensors track every console. Routes are adjusted in real time to avoid weather, customs delays, or port congestion. Because when Sony does a global launch, they don't mean over a few weeks. They mean one day, one moment, a shared human event where millions of players from Tokyo to Toronto unbox their console together. But all of this, all the robotic precision, the silicon engineering, the thermal mastery, none of it starts with an assembly line. It starts in a room, a meeting, a whiteboard. That's where the lead system architect Mark Cerny begins. Every new console starts with a list of things the previous one couldn't do, a wish list, a backlog, but more importantly, it's in a conversation with the developers, the ones building the games. They say what they need, what held them back, what they want next, and sometimes those meetings are brutal, but that's where the breakthroughs happen. One of the biggest requests? An SSD. Developers had been begging to ditch the rusty, spinning media of hard drives for years. Game data, where models, textures, animations, was being bottlenecked. That's why PS5 uses a custom NVMe SSD with a read speed 5 to 10 times faster than what developers even asked for. That means no more elevator loading screens, no more narrow passageways just to hide background loads. Fast travel that actually is fast, but an SSD that fast needs a matching data pipeline. That's why Sony built a custom I/O architecture with invisible compression. Developers don't even have to manage the data compression or decompression. It's all handled by a dedicated unit in the custom chip. The result? Games are smaller but more detailed. Subnautica dropped from 14 gigabytes to 4 gigabytes. Control, Ultimate Edition, was cut nearly in half. Miles Morales, even with higher resolution assets, ended up smaller on PS5 than PS4. The same level of obsession went into the CPU. 8 Zen 2 cores, not just for better graphics, but for smarter AI, more responsive physics, and richer simulation. In games like Returnal, there are thousands of projectiles on screen at once. In Destruction All-Stars, the vehicle deformation is handled by the CPU in real time. Even though some devs wanted 16 cores, they backed off when told it would shrink the GPU. Because the GPU, that's where the eye candy lives. The PS5 GPU is a customized AMD RDNA 2-chip running at 2.23 GHz with 10 teraflops of compute power. That translates into realistic lighting, detailed skin textures, and subtle facial animations that just weren't possible before. It also supports ray tracing, something that wasn't even high on the wish list because developers didn't think they'd have enough horsepower to use it. But Sony delivered, and at their very first PS5 showcase, 6 games already used it. Ray trace shadows, reflections, global illumination, it's all here. Then there's audio. PS5 includes a dedicated unit for Tempest 3D audio. This isn't just better stereo. It's full spatial audio that creates a feeling of presence, like sound is actually coming from around the player. Rain sounds like it's falling in the room. Footsteps in the distance feel directional. And it doesn't require special headphones. Any stereo set will work. Even the controller, the DualSense, reflects this same philosophy. With adaptive triggers and haptic feedback, players can feel the difference between pulling a bowstring and firing a gun. When a weapon jams in Deathloop, the trigger physically locks. When riding a horse in Ghost of Tsushima, the feel of stone versus mud comes through the vibration. All of these features come together in one seamless experience, but none of it works without that custom robot in Kisarazu, quietly applying a bead of silver liquid metal no bigger than a matchstick head. Because in the end, perfection isn't just about power. It's about the invisible details, the stuff no one sees, the parts that make it feel like the future is in your hands. And that's the real secret. The PS5 is a machine built by machines, but it's made for people. The robots build the console, but it's the human connection, the midnight unboxing, the first button press, the shared moment across time zones that gives the PlayStation 5 its soul. Thanks for watching. For more deep dives into the engineering, design, and storytelling behind the world's most iconic tech, hit that subscribe button. Like, comment, and share if you learned something new.